Hello everyone. Thank you for joining us. In today's webinar, we will learn how the multiphysics simulation capabilities of HFWorks can be used to design and analyze RF and microwave heating systems by considering the metallic and dielectric electromagnetic losses. We will also learn how to leverage the powerful features of HFWorks and SolidWorks to investigate the impact of geometry, material, and RF microwave power variations on systems performance. Before discussing today's agenda, let me introduce us. My name is Cal and I handle sales and marketing division of our company. My colleague Asma works as a senior application engineer for EMWorks. She has an extensive knowledge in electromagnetics and multiphysics analysis. She will be delivering the technical part of today's webinar. I would like to highlight few points. During this course of presentation, if you have any questions, please feel free to use the chat window to type in your questions. We will answer them at the end of the presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Moving on to the agenda of today's presentation, I will briefly talk about our company EMWorks and various products we offer. Then my colleague will present the technical part of today's webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. Now let us take a quick overview on our company EMWorks. We offer 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of computational electromagnetics. In addition, our products are gold certified by Dassault Systems SolidWorks Corporation since the year 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. Now let us take a quick overview on EMWorks products. We offer 4 products with various add-ons covering a wide frequency range. Our first product is called EMS, which is used for electric and magnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, solenoids, circuit breakers, transformers, and electrical machines. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high-frequency and high-speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, and waveguides. Our third product is called EMWorks 2D, which currently offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is Motor Wizard software, which is a template-based motor design tool. It currently offers analytical and finite element analysis of brushless DC electrical motors. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, we will demonstrate RF and microwave heating simulation using HFWorks software. EMWorks offers 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs, our licensing structure is annual based. Now I would request my colleague Asma to take over and present the next part of this webinar. Thank you.
Thank you, Kar. Hello, dear attendees. First of all, I want to thank you all for joining us today. I am Asma, Senior Application Engineer at HFWorks, and today I'm going to represent you the technical part of today's webinar about RF and microwave heating simulation using HFWorks tool inside SolidWorks. Let's have a look in our agenda for today. We will start with an overview about HFWorks tool inside SolidWorks. Then we will go through a quick introduction about RF and microwave heating, the main principle and design challenges of these heating technologies. Next, after a quick live demonstration of HFWorks interface inside SolidWorks, we will go through a detailed analysis using HFWorks simulation solution to investigate the main design challenges of the studied heat process with two different examples, the first example for RF heating and the second one for microwave heating. And finally, a conclusion. Let's start by introducing our software. What is HFWorks? HFWorks is a 3D field simulation software fully integrated inside SolidWorks for RF, microwave and wireless application. It is an add-in inside it, allowing the user to work on both CAD and simulation within the same interface. So to start with the CAD modeling, SolidWorks provides a powerful parametric CAD platform treating all geometry types and allowing a quick building and editing of your geometry or importing your own geometry inside it, with the ability to build multi-geometrical configurations. Next, when your model is ready, you can switch to Simulation tab and start by the pre-processing steps like the frequency sweep setting, the material assignment, the needed boundary conditions, the parameterization setting in case of parametric analysis, and finally the step of meshing using many different mesh options provided by HFWorks for manual and adaptive meshing. Then the run step with many available options like the run of the multi-selected study, the autosave after run, and so on. After the run is done, you get your results in terms of circuit results or 3D and 2D field plots. We'll check more details later what kind of results we can get with HFWorks. And finally, if you want to have a multiphysics coupling, it can be done using post-processing thermal and structural coupling, allowing thermal stress analysis of your device with the ability to rerun your electromagnetic part with the final deformed structure. Actually, with the structure with the deformed electromagnetic will be available soon in a beta version release. As we said, HFWorks covers a wide range of applications like antennas with many types like the printed antennas, waveguide, horn, wired, etc. S-parameter analysis for waveguide, teeth, directional coupler, isolator, circulator, etc. Also with the time domain reflectometry analysis, and finally we resonance study for studying dielectric resonator, etc. As we already mentioned, HFWorks comes with an integrated electrothermal and structural analysis, providing a powerful and complete multi-physics analysis for electronic products, ensuring their electrothermal reliability, which is available for antennas as parameter and TDR analysis. Next, let's have a quick look on the sequential process of the simulation inside HFWorks study with multiphysics analysis. As we already mentioned, we start with the electromagnetic simulation, which could be done with single or frequency sweep with the ability of parameterizing your geometrical simulation variable and also wavelength parameterization. During it, a power scaled conductor and dielectric losses are computed and visualized. Those will be then fed to the post-processing thermal solver to compute and plot steady-state and transient thermal solutions. By the same way, Temperature results could be fed to the structural solver to compute thermostresses generated inside your electric device and visualize it by a mechanical deformation of the structure under the user-defined power excitation. At this step, HFWorks allows to recompute the electromagnetic parameters of the deformed model to predict how the thermal loads could affect the electromagnetic performance of the analyzed model. In addition to that, rich material and multiphysics demo libraries are available to facilitate your simulation tasks and also satisfy your needs as a designer. For today's webinar, we are going to work on the electromagnetic and thermal solutions of the RF and microwave heating process. So, let's go through a small introduction to this topic. Many high-frequency heating applications were built based on transformation of electromagnetic losses into heat, which outperformed the limitation of traditional heating methods. RF and microwave heating are ideal for process heating, a situation where the speed of heating, the product consistency, and the low operating cost are key competitive advantages. They are more reliable, flexible, and energy efficient than the other alternative, and the most important thing, they are more affordable. These two high-frequency heating technologies work relatively the same way. Heat is generated when the product is passed through an alternating electromagnetic field due to the product losses. This electromagnetic field creates vibration and rotation in the polarized molecules inside the material, so this friction between molecules increases the temperature of the heated part. Both technologies are based on the volumetric heating, and the main difference is related to their wavelength and operating frequencies. For RF heating, it operates from 3 kHz to 300 MHz, and for microwave, it operates from 300 MHz to 300 GHz. Now what about the applicator design of each type? For RF heating, RF energy is generated by an RF generator. Radio frequency moves from an electrode to another inside the cavity and through the treated material. Electric field in this technology is uniformly propagated in a straight direction. For microwave heating, energy is generated by a microwave generator and should be guided by waveguides up to a closed cavity. Electric field in this technology is randomly propagated inside the cavity. Here we have a brief comparison of the main characteristics of RF and microwave heating processes, which are summarized by the next table. We have the general frequency range for each type, and also the allowed frequency for industrial, medical, and domestic uses. Each technology has its own application domains, but the main characteristics that strongly define your decision about the right technology to use are listed in this last four criteria. For RF, thanks to their longer wavelength, radio frequency can penetrate deeply inside the heated load, which allows to heat thick products, which is not the case for microwave technology. For this last one, it is highly effective for treating products at higher heating speed with no geometrical limitations. Thanks to their ability to heat uniformly, microwaves are also used to quickly heat or dry industrial materials or foodstuffs. Now for the application domains, RF and microwave processing could be used to heat any dielectric material, and most food products are dielectrics, so they are used for food processing like pasteurization, melting, cooking, etc. And for the industrial applications, they are used for baking and drying freshly baked products and wood, for tempering and thawing, and even plastic welding, bonding, and tube sealing. For biomedical applications, they are used for microwave ablation therapies of tumors or local tissue heatings, etc. And finally, For agriculture applications, they are used essentially for drying or microwave treatment of animals' fodder or oil extractions, etc. As a designer or an engineer, before moving to the concrete manufacturing and the use of your heating technology, many factors should be taken into consideration and which affect strongly your desired heating profile and rates. Those factors could be related to the geometrical parameters of heating applicator or heated load, like the load geometry position or the applicator design, or could be related to the main heating process parameters, like the excitation power, the frequency, the heating period, etc. HFWorks tool, with its great simulation features, presents a perfect solution for the design challenges of RF and microwave heating technology. But before moving to the simulation, let's have a quick demonstration of HFWorks interface inside SolidWorks. And here we are. We have here our SolidWorks interface with the studied example of RF heating that we will use for our simulation. Here we have geometrical parts of our CAD model. As we said, HFWorks is fully integrated inside SolidWorks. We can activate it from this add-in window. So just checking here HFWorks. Once it is checked, a new HFWorks tab will be added here for the simulation, from which we can create our study. As we said, we have 4 modules inside HFWorks. We have the antenna study, the S parameter, the TDR, and finally the resonance. So if you want to create new study, just click here S parameter. A new study will be created. We start with general properties. Like here, we have to choose the type of solver to use, direct or iterative. We have also to set the accuracy level, first and second level. If we want to add the parameterization, we have to check this, just this checkbox. For the results, if we want to see only port solution or also have the 3D field data. For the second tab, it is used for frequency setting. If we want to have only one frequency or frequency sweep, fast or discrete sweep. Next, we have the meshing step. We have the adaptive and manual meshing with many advanced options. And finally, the coupling case analysis for multiphysics analysis. For our case, we have the thermal coupling. So once our study is created, an HFWorks study tree will be added here, like you can see from the already defined study. So we have many sections. We start with the materials. If you have to only assign your materials by right-clicking, apply materials. A well-organized and rich library will be opened, like you can see here. So you assign your material for each part. Next, you have to define your boundary conditions, the port, etc. We have many boundary conditions, electromagnetic boundary conditions according to your analysis type. Next, you have to define your mesh setting. As we already said, we have the manual and adaptive meshing with many advanced options. And after that, you have to just run your study and a section of results will be created. Like you have here, we have the electric results, the magnetic results, the loss distributions. Also, you can compute the total loss quantity for dielectric and conductor losses. We have also the circuit parameters for tabular and 2D plots, etc. Now, once you are checking the thermal coupling from the study property page, we have here the post-processing coupling case for the thermal analysis. You can create many coupling case for each type. You can even create your steady-state thermal or transient thermal. For example, if you want to create transient thermal coupling case, you have here to define your frequency at which you want to solve your thermal. Also define here your excitation power for each excited port. You have to check your excited port. You have here also the type of thermal loads that you want to use inside thermal. And setting, like here, if you have here the step loading, we have 2 types of thermal loading. You have the step loading and also the progressive using the ramp loading. So you have just here for each time range, you can define your end time, the heating period, the time increment delta T, and finally the end load level. Since we have here ramp loading, we can define our scale of loading. And also, if you want to create more than one time range, you have to just right click, add, and you will add another time range with the defined end load level. Finally, when validating your coupling case, a new coupling case will be added here. You have to just define your thermal boundary conditions, the temperature, convection, heat flux, volume heat, etc. We have also the radiation. And just right click and run. We already have here the solved thermal coupling for the first frequency. We have the thermal results, etc. And this is our sequential process for creating an S-parameter study with thermal coupling. Let's come back now to our simulation solution. During it, we will work on the effect of each design challenge affecting the heat of the load for the studied RF and microwave technologies. Let's present briefly our two examples. For the RF heating, which is operating at 27.12 MHz, it is dedicated essentially for industrial use in drying food products. The studied model is formed by an RF cavity chamber limited by two parallel aluminum electrodes, a polystyrene sheet deposited on the bottom electrode and supporting another polystyrene container, which is containing 3 soybean flour layers to be RF heated. For its high heat resistance and portable characteristic, polystyrene is widely used for in the food processing and packaging industry. For the microwave heating, we have a 245 microwave oven used for domestic use. The CAD design was made using SolidWorks, and it is containing a rectangular microwave oven filled with air and connected to a 245 microwave source via a rectangular waveguide operating in the TE10 mode. Near the bottom of the oven, a glass plate is inserted with the heated sample. Let's start now with our first factor, which is frequency. It is the most important factor that defines which heating technology and applicator design that the designer should use. We already selected the right applicator design for RF and microwave domain, but let's check the heating profile and rates for the other allowed frequency with one RF applicator without modifying its geometrical dimensions. So, we already presented the RF heater mainly, used for 27 MHz heating. So we will try with the first run with the frequency sweep using 3 different frequencies, essentially used for industrial food processing, which are the 13.56 MHz, the 27.12 MHz, and finally the 40.68 MHz. The port boundary conditions are applied to the opposite air faces shown by the following figure. Let's move now to the SolidWorks interface. So we have here our study already solved. We start with electromagnetic results and then the coupling case with thermal results. So let's check our electric field distributions. Now for the first frequency of 30 MHz, we can animate the variation of electric field versus phase. As we can see here, it is alternating between 0 degree and 360 degree. As we can see that the electric field is alternating between the top and the bottom electrodes, which is due to the rapid change in polarity. So the electric field here is uniformly propagated in straight direction, which is characterizing the RF heating technology. With the same thing, we can here check the fringe plot of the electric field inside the heated loads for the 3 flour layers. For an excitation power of 6 kW applied to the first part, and also we can here switch between one frequency to another, and the plot is automatically updated. Same thing for 27 megahertz. Also the electric field distribution and values are updated. Let's move now to the thermal results. For each frequency we solved the coupling case for transient thermal, and for the heating period of 5 minutes we got this temperature distribution. For the first frequency we have 34 degrees Celsius. Same thing for the 27 megahertz. After 5 minutes of solving we have 42 degrees of Celsius. And finally for the 40 megahertz. So let's come back to our presentation to summarize those results. So the following table is summarizing the obtained results for each frequency. For an excitation power of 6 kW, conductor losses generated inside the metallic electrodes are neglected compared to the dielectric losses inside the heated food loads. And heat rates are proportional to the frequency according to the obtained temperature results for the same excitation power and for the same geometrical dimensions. For the same frequency factor that we are treating, let's check now the results for the microwave oven. For the heated load we will use simplified geometry, which is a cylindrical sample, and in order to reduce the computational time, only half of the model will be simulated using the HFWorks symmetry boundary conditions. As a result of it, the simulated revealed the following temperature distributions for an excitation power of 500 watt and the duration of heat equal to 1 minute. As you can see, temperature is the same for the full and the half model using symmetry boundary condition. As we said, to reduce the simulation time, we can use the half example for the rest of our investigation of the microwave oven. For this half microwave oven, the electric field distribution for an excitation power of 500 watt is shown by the right figure at phase equal to 80 degrees. The electric field distribution is perfectly symmetric inside the cavity oven at this phase. HFWorks allows also to compute and visualize the distribution of conductive and dielectric losses, which are defined by the left figures. The metallic losses are localized at the outer surrounding oven walls, and the dielectric losses are limited to the heated sample made of cold material, with the maximum values concentrated in the center. Also, with the total loss feature of HFWorks, we can also compute the dielectric and conductor loss quantities in your structure. For our case, for an excitation power of 500 watt, we have 321 watt are wasted in the dielectric. Conductor losses are insignificant here. Now we come back to our design challenge slides to move to the second factor. So the second important factor, which is the applicator design. How does the geometrical dimensions of your applicator design affect the heat profile? To answer to this question, we will check with the RF applicator design. Now, using parameterization feature inside HFWorks, coupled with the transient thermal to parameterize the distance between the two loaded electrodes. 5 different scenarios defining the electrode gap variation between 100 mm and 250 mm for a heating period of 5 minutes. The simulation gives the following results. The electric field animation is showing a decrease in its magnitude with increasing the electrode gap. For the dielectric loss variation shown by the top figure, we can easily notice that they are inversely proportional, and there's a big difference in induced losses between the first and the final position, which affects automatically the temperature results. The heat profile is more uniform, as we can see from the temperature distribution across the floor layers for the first scenario, which means when the electrode gap is minimum. So now to conclude, The distance between the loaded electrodes, which includes the heated load, affects strongly the quantity of losses induced inside it. They are reduced more than 7 times when decreasing the electrode field 1 time and a half. So it is very important to adjust your applicator dimensions based on your needs, which could be very easily done using HFWorks simulations. Let's come back now to our factors. We will move to the third factor that the designer must take into consideration, which is the geometry and the position of the heated load. For this reason, we will use now the microwave oven example to analyze the effect of this factor using HFWorks. Under the same heating conditions and using the same material inside the studied microwave oven, we selected 4 different configurations to be tested using SolidWorks multi-configurations as following. We have the cylindrical, rectangular, spherical and finally irregular shape using a chicken design. As we can see from the heating profile, all load shapes have the same temperature distribution since we didn't change the material, with the maximum heat increasing from the center to the outside. This behavior describes well the dielectric heating, in which the heat is dissipated inside the irradiated sample and transfers from the medium to the outside. Now what about the load position? Let's check the case of multi-loads. In the right figure, we have the electric field animation versus phase for an excitation power of 500 watt. The left side figures are showing the temperature distribution for the transient thermal solution during 1 minute of heating, and below it the steady state solution. As you can see, we obtained a non-uniform heating profile and rate across the 3 loads, which confirms the importance of the load position inside the microwave cavity and its effect on the achieved heating. A second analysis of the effect of load position on heat distribution is done by varying the position of the heated load across the central plane from the right to the left. The following animation plot is showing the variation of dielectric loss distribution inside the load versus its position. As you can see, the distribution is non-uniform and changes from one position to another, which confirms the random propagation of fields inside the cavity for this type of heating. Now, for the temperature results, same thing is noticed. So to conclude, maximum temperature values and distributions could not be predicted according to the load position inside the microwave cavity, which could not be the case for RF heating design, since the standing waves did not cause heating uniformity problems for the product, because the conveyor movement in most cases is in the same direction as the standing wave. Another important factor that defines the heating rate and the final achieved temperature of your load is the excitation power. With one main electromagnetic study, HFWorks allows to solve multi-thermal analysis with different input powers for both steady-state and transient thermal solutions to optimize your heating process. For an excitation power range varying from 100 watt to 1 kilowatt, and for a heating period of 1 minute, we got the following temperature variation versus input power. Maximum achieved temperature is linearly proportional to the excitation power, which is well predicted, and maximum temperature is always concentrated with the load center without affecting the heating profile. Another important factor which is strongly linked to the excitation power is the heating period. Trying to find the best formulation between the needed input power and the heating time presents a real challenge for high-frequency heat processing, which could be easily done using the transient thermal solver of HFWorks with its flexible and advanced options and boundary conditions. We come now to our final factor, which is the energy focusing, which means the geometrical and process factors that allow to focus the maximum of lost power inside the heated sample and get more uniform heating profile. This factor includes the number of excited parts for multi-part configurations, as well as the excited phase and mode for each part. Let's check now with our studied example how this factor can affect the heated behavior. We start with the microwave cavity oven. We use for this case the full model. When we have a dual symmetric part configuration like shown here, HFWorks allows a post-processing power handling of your results without the need of rerunning your analysis for each scenario. When exciting only one part, we notice the non-symmetric distribution of temperature across the half of your load. But this behavior is improved when exciting simultaneously both parts with 0-degree phase, like you can see from the central figure of the temperature distribution across the load, which is not the case when adding a phase of 180 degrees between the part excitation. When exciting both parts, we divide the power between the two opposite parts. We got higher heat rate than only one excited side. So, to guarantee a symmetric heating profile with higher temperature, it is better to use more than one excited part. Same thing done with 4 and 3 parts. Exciting all parts together guarantee the uniform heating profile of the sample, as you can see from the following temperature results compared to only one excited part. Same thing could be done for the second example of RF heating. Here we have two opposite parts. When exciting both parts at the same phase and with 180 degrees phase, the electric field is much more higher within the flower layers when both parts are excited at the same phase, and the distribution is more uniform compared to the second case, since the standing alternating waves are concealing each other versus phase. As a result of it, the sample is not heated by the same way when a 180-degree phase is added between the excited parts, and it achieves very small heating rates because of the concealing factor introduced by the phasing. We conclude now with these results. HFWorks for SolidWorks covers different design issues and challenges posed by the RF and microwave heating processes. It provides powerful and complete multiphysics analysis of electronic products, ensuring their electrothermal reliability. Through this webinar, we tried to show you how HFWorks and SolidWorks allow to analyze the effect of geometrical and process parameters for complicated heat processing based on RF and microwave energy. Finally, thank you all for your time and attention, and I hand over again the screen to my colleague Cad.
Thank you, Asma. To refresh our memory, let us take a quick overview on HFWorks modules and add-ons. HFWorks software offers 4 modules: antennas, S parameters, resonance, and time domain reflectometry. In addition, we offer various additional features like thermal analysis, parameterization, and capabilities such as ECAD import and power handling. To get information on the software pricing, you can connect with me after this webinar. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer 3 products: EMS 3D, EMWorks 2D, and Motor Wizard. These products can be used to design and simulate applications such as cables, insulators, bus bars, actuators, solenoids, eddy current braking systems, wireless charging devices, transformers, and electrical machines. Within high frequency category, we offer one product, HFWorks. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, and connectors. EMWorks offers various free learning resources. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMWorks website. Select the appropriate category, fill in your information, and submit your request. One of our representatives will reach out to you soon. I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on this product. Thank you.